Okay, in this problem, I've got air in a 2 cubic meter rigid insulated tank. So the volume stays constant. That's what rigid means. Insulated means Q equals 0. Okay, it does have a paddle wheel, so work can be added to the system. And it's initially at 302 bar, and it's stirred until it gets up to 500 degrees Kelvin. So I first want to find the final pressure. Okay, so to find that final pressure, remember volume is constant, right? So again, I have the equation PV equals MRT. Okay, well, if volume, mass, and this is all constant, which they are, right? Because it's rigid, it's the same amount of stuff. R is always going to be constant. Well, then just P2 over P1 equals T2 over T1, right? Plugging in what I know about my temperature, what I know about my pressures, I can find that final pressure, P2, equal to 3.33 bar. Okay? So that'll give me that final pressure. Again, I can use this relationship just because I have a constant volume process here. Okay. Now, in order to find the work in the entropy production, I'm going to need to find the mass within here. So again, that mass then is just going to be using this equation where P is, I'll just use the initial conditions, is 2 bars, so that's 2 times 10 to the 5th times V, which is 2, all over R, which is 8314, divided by, this is air, so 28.97. Okay, times the temperature, which is 300. Okay, so I just use the ideal gas model to figure out the mass, and I find the mass to be 4.65 kilograms. Okay, now again, I'm using that because I want to find the work. Okay, now to find the work, okay, I'm going to use the first law equation, which is basically Q minus W equals delta U. Now, Q is 0 because it's insulated. So there's no heat transfer. So the work is nothing more than the mass times the change in specific energy. Okay, so that gives me 4.65. Now I just need to look up U2 and U1. That would be for 500 and 300 Kelvin for air. So I go into my table. 500 Kelvin, U is 359.49, and at 300 Kelvin, U is 214.07. So I can go ahead and jot those guys down there. So again, I have 359.49 minus 214.07. Again, I've got this minus sign over here. So when I do this subtraction, right, I actually kind of have to flip these anyway. I get a work that's going to be negative 676.2 kilojoules. So that is the work that's being done here. Okay. Now, in order to find the entropy production, I'm going to go and use my second law equation, where my second law equation is essentially delta S equals del Q over T, right, plus the entropy production. Again, this is what I'm looking for. Okay. Delta S, of course, is just that mass times S2 minus S1. Okay, where, remember, for air, this is actually that mass times S2 naught minus S naught 1 minus R over the natural log P2 over P1, like so. Now, the other half of the equation, again, this goes to 0 because, again, it's insulated. There is no heat transfer. So my entropy production equals all of this. So I can go ahead and write that equation. So I'm going to take 4.65, which is the mass. Now I need to look up S02 and S01, which again is 500 and 300 Kelvin. So I go in here and I have 500 Kelvin, so S02 is 2.219, and at 300, S naught is 1.70. So I can plug those values in here, 2.1952 minus 1.70203 minus R, which again is, 8.314. So I want it in kilojoules divided by, again, this is air, so 28.97 times the natural log of P2 over P1, which again is, we calculated 3.3. P1 is 2. So that big equation gives me my entropy production, sigma, which is 1.724. Now, sigma has to be greater than 0, which it is. Sigma cannot be a negative number, so if I'd gotten a negative number, something would have been wrong, but I would have been okay on this one. Okay, and again, sigma just equals delta S because it's insulated, Q equals 0. Okay, and delta S, remember, for air is that S naught minus 2 minus S naught 1 minus R times the natural log of the pressure ratio.